Let me begin today's IEICE webinar. First, I sincerely thank the IEICE International Committee for this opportunity. In particular, I am deeply grateful to Professor Yoichi Sato from the University of Tokyo for his kind proposal. The title of today's talk is Recent Progress in Medical Foundation Models. I am Akinobu SHIMIZU from Tokyo University of Agriculture and Technology. My talk connects to a previous IEICE webinar by Professor Fujita from Gibb University, as shown here. In his lecture, he covered the history of AI-based computer-aided diagnosis in medical imaging, mainly up to 2022. Today, I will focus on medical foundation models, which have seen rapid development since Professor Fujita's presentation. Here is a list of survey and review papers on medical foundation models that I used to prepare this lecture. Please refer to them if you'd like to learn more. Let me now give you an overview of today's lecture. I will begin with an introduction to recent progress in foundation models. I will explain not just how the model have evolved quickly, but also why this evolution has happened. Then I will talk about the current foundation models used in the medical field, which include clinical large language models, foundation model for medical image analysis, text-to-image foundation models for omics, and Japanese medical foundation models. I will end with some thoughts on the future and the key challenges of medical foundation models. First, let me define a few key terms. As many of you know, artificial intelligence includes machine learning, which includes neural networks, and deep learning is a part of it, but it has had a huge impact on medical image analysis. I think this visual represents the current situation quite well. It is highly inflated in size, while still being a part of AI, machine learning, and neural networks. Today, I think this updated diagram is more appropriate. Foundation models are now playing a key role in deep learning. Some well-known examples are large language models like ChatGPT, vision language models that combine images and text, large multimodal models that handle speech and other inputs, and generative models like Stable Diffusion. Recent reviews say foundation models are now at the peak of inflated expectation. This chart is called the hype cycle, published by the US think tank Gartner, focusing on generative AI. It shows 5 stages from innovation trigger to the plateau of productivity. Many technologies rise quickly, get overhyped, and then fade. Some disappear, but the truly valuable ones survive and reach the plateau of productivity. Foundation models, shown in the blue circle here, are expected to reach the plateau of productivity within 2 to 5 years. So what exactly are foundation models? The term was first introduced by the Stanford Institute for Human-Centered AI, which defined them as AI is undergoing a paradigm shift with the rise of models trained on broad data that can be adapted to a wide range of downstream tasks. We call these models foundation models. Current flagship models include BART, GPT, and so on. From a technical perspective, foundation models are not new. They are based on deep neural networks and mostly self-supervised learning, both of which have existed for decades. But today's foundation models are much larger and more powerful than before. For example, GPT-3 has 175 billion parameters. It can perform many tasks without being explicitly trained for them, simply by using natural language prompts. So now let me show some examples of foundation model. Sora is a family of ChatGPT, which can create this movie with this prompt. Beautiful snowy Tokyo city is bustling. The camera moves through the bustling city street, and so on. Unfortunately, this YouTube video could not be included in my lecture, so please watch it later from the URL on the lower right. You will enjoy the high resolution and beautiful movie. This slide introduces several examples of foundation models in medicine. As shown in this pie chart, most recent foundation models mainly use X-ray and CT images. This is mainly because the databases used for training often contain these types of images. However, the scope is gradually expanding to include eye fundus images and MRI images as well. Also, while the main application has been report generation, these models are now being used for other tasks, such as image classification, segmentation, and image generation. Now, it is well known that many of these foundation models are built using transformer. For example, BART is based on the encoder part of the transformer, while GPT, PARM, and Llama are based on the decoder part. As a result, we have models specialized in text understanding like BART, and models focused on text generation like GPT, PARM, and Llama. This graph shows the number of model parameters on the vertical axis and the year on the horizontal axis. The colored circles represent medical foundation models. The size of each circle shows the size of training data. The color indicates the type. Orange means encoder-only models like BART. Blue means decoder-only models like GPT and PARM. And green means models that use both. You can see that medical foundation models started with BioBART around 2019, followed by BioMegatron and Gatatron, and then rapidly increased after 2023. Larger models developed more recently are often decoder-based models shown in blue. This slide shows a tree diagram of medical large language models. Around 2019, most models were based on BART and used encoder. Over time, decoder-based models like GPT and PARM started to increase. Recently, models based on Flamingo, which use both encoder and decoder, have also appeared. This chart shows how model sizes have changed for BART type, ChatGLM Llama type, and GPT Palm type models. The vertical axis uses a logarithmic scale, so you can see that the model size have increased by order of magnitude around here. Some models now have more than 100 billion parameters, which is even more than the number of neurons in the human brain. The performance of large language models improves as their size increases. This graph shows USMLE scores from the MedQA datasets on the vertical axis. Solid lines are open source models, and dashed lines are for closed models. Some models already exceed the passing score. Of course, passing this exam does not mean AI can be a doctor. To discuss whether AI is equivalent to a physician, serious discussion is needed about what humans learn in medical school and what is not tested in the exam. This table shows the main application of foundation models. From top to bottom, they include multimodal medical foundation models capable of processing videos and audio input, vision-based medical foundation models targeting omics, and finally, clinical large language models. It can be seen that clinical large language models were the first to emerge and have rapidly expanded in application since around 2022 to 2023. Why did they grow so fast? Of course, the development of the transformer model had a big impact, but there are other key reasons. The expansion of dataset size, the evolution of self-supervised learning for handling larger datasets. The double descent theory encouraged the model size expansion, and scaling law have led to the expansion of GPU, datasets, and models. This expansion of data, models, and GPUs have also accelerated the development of foundation models. The following slide shows specific examples. Let's first look at the datasets used to train and evaluate foundation models. Since around 2016, large databases of radiological images and diagnostic reports have been developed. These are essential for building clinical large language models. Most datasets include chest X-rays and diagnostic reports, but more recently, multimodal datasets such as CT, MRI, and ultrasound images have also become available. These are another examples of medical image and report datasets. The first datasets uses structured labels created from free text report. Later database added features like annotation labels, bounding box, and even graph-based representation of report contents. These improvements help foundation models better understand the relationship in medical data. However, preparing large datasets with detailed annotated labels is still very difficult. In such cases, self-supervised learning becomes very important. This method allows us to use large amounts of data efficiently, even if the data is not labeled. Another key point is the discovery of the double descent theory. Before this theory, it was believed that making models too large would increase the risk of poor performance on unknown data. But double descent theory showed that when the model size becomes even larger, the performance improves again. This discovery encouraged researchers to build even bigger models. In summary, this scaling law shows us that better performance can be achieved by using more data, making the model bigger, and using powerful computers. This is why research on foundation models has become so active in recent years. Now, let's look at some specific examples of foundation model in medicine. I have grouped the models into several categories based on their main applications. Although foundation model can be used for many different tasks, I will explain them based on their primary applications to make things easier to understand. Since I cannot introduce all the models in these lectures, I will focus on the most important ones. These are marked with red lines in the list. Let's start with clinical large language models. Here, I will introduce three examples: BioBART, Meditron, and Flamingo CXR. BioBART is one of the earliest foundation models in the medical field. It was developed around 2019 to 2020. The model had 345 million parameters and was trained on 4.5 billion words from PubMed and 13.5 billion words from PMC. It achieved excellent results in tasks such as biomedical question answering. This model was the first to show that large language models can work well in medicine. Next is Meditron. It is a recent model with 70 billion parameters released around 2023. Meditron is based on Llama 2 and is open access. It was trained using 48.1 billion tokens and showed better performance than GPT 3.5 and MedParam. In fact, it performs similarly to GPT-4. This model is one of the most powerful open access medical LLMs today. Flamingo CXR is a recent model based on Google DeepMind Flamingo. It can generate both findings and impressions for chest X-ray images. Benchmark tests showed that it performed much better than previous state-of-the-art models. Another important contribution of the Flamingo CXR study is that it carefully examined whether collaboration between doctors and AI is truly beneficial. In the assistive scenario, the AI first generates a report and then a human expert checks and revises it. The result shows that this collaboration improves both accuracy and usefulness. Next, I will introduce two models with different main applications. MedSum is mainly used for segmentation, and BioMedClip is used for classification and so on. Let's start with MedSum. SUM stands for Segment Anything Model, which was released by Meta in 2023 as an open source model. MedSum was trained on 1 million images from various body parts and imaging modalities using mask pairs. The panel in the lower right shows the results on external datasets. The MedSum outperforms both SUM and UNet in segmentation accuracy. This model can be applied to many kinds of segmentation tasks. Next is BioMedClip, an open access foundation model developed by Microsoft. As the name suggested, it is based on CLIP. It uses two types of encoder, one based on BART and the other on GPT. The model was trained on 15 million image text pairs. It can be used for classification, image retrieval, visual question answering, and even privacy-preserving data analysis. In the classification scenario, BioMedClip shows better accuracy than PubMedClip and OriginalClip, especially in zero-shot classification tasks. It also performs significantly better than previous models in image retrieval tasks. Now let's move on to generative models that create images from text. Not long ago, GANs, generative adversarial networks, were the standard. But recently, diffusion-based methods have become more popular. In particular, after the release of Stable Diffusion in 2022, many studies have used this method for generative AI in the medical field. Stable Diffusion can generate detailed images based on text descriptions. The model works in two steps. It first adds noise to the image, the word path, Then remove the noise to reconstruct the image, the reverse path. Since both the code and model weights are publicly available, it has been widely used in many research projects. It has been used in the field of medical image analysis, for example, to generate skin diseases. The diffusion model is conditioned using the output of encoder processed with the input text prompt. And finally, synthetic images are generated using a variational autoencoder. The image on the right shows the images generated from each prompt, for example, basal cell carcinoma, which demonstrates its effectiveness in capturing the characteristics of lesions and generating diverse disease images. In this study, the generated synthetic images were carefully selected by this process and used to augment a classification task. The results show that replacing half of the original image with synthetic images actually improve the classification performance. Another example of stable diffusion in medicine is Röntgen, a model that generates chest X-ray images from text. It uses a conditional unit with embeddings created from short free text medical prompts by our text encoder. The decoder in the stable diffusion pipeline then maps the denoised latent vectors into pixel space. This process creates high-quality and diverse chest X-rays that match the described imaging features. The figure on the left shows examples of generating pleural effusion images with different features. You can see that the generated images reflect differences in size and position based on the image input prompts. On the right, there are detailed prompts used to generate even more diverse types of lesions. For example, in the top right image, the prompt is edema, and you can clearly see the fine features like those marked by white and black arrows. Lastly, in this section, I would like to introduce SCBART, which was published in Nature Machine Intelligence in 2022. SCBART followed the same approach as BART, with pre-training and fine-tuning. It learns general gene-gene interactions by pre-training on large amount of unlabeled scRNA sequence data. Then it is fine-tuned to annotate specific cell types based on user-specific database. Benchmark studies show that SCBART performs well in many areas: cell type annotation, discovery of new cell types, resistance to batch effects, and model interpretability. It is a powerful model for understanding single-cell biology. Now, I would like to introduce medical foundation models developed specifically in Japanese. Why do we need medical foundation models developed in Japanese? There are three main reasons. First, linguistic and syntactic differences. Japanese medical text often includes unique expressions, technical abbreviations, and ambiguous phrasing. These are difficult to handle with a combination of English foundation models and translation models, which may cause misunderstanding and reduce performance. Second, differences in medical systems and medical practices. Japanese medical guidelines, tests, and prescription methods are often different from those in English-speaking countries. So we need to train models using Japanese data for practical use. Third, compliance with legal systems, ethics, and social requirements. In Japan, AI for healthcare must be trained and evaluated with domestic data to meet requirements for accountability and ethics. English-trained models may not meet legal or social expectations in Japan. For these reasons, we believe that the Japanese foundation models are essential for Japanese healthcare. Let me explain the recent development of large language models for Japanese. This figure shows LLMs developed between 2020 and 2024. Yellow indicates closed source models. Orange shows open models, and red represents open models trained from scratch. Since 2021, open source models trained from scratch in Japanese have been developed. Recently, even larger models of this type have been released. Medical LLMs for Japanese have appeared since the end of 2023. So now let me show the details of Japanese medical LLMs in the next few slides. The first Japanese medical LLM was a fine-tuned version of an existing LLM trained on Japanese medical datasets. In 2023, JAMIT was developed based on Llama 2 and fine-tuned using Japanese medical Q&A dataset. Later model used multiple 70 billion parameter Japanese LLM. Instruction tuning with Japanese medical questions greatly improved their ability to answer national medical licensing exam. After that, models using continual pre-training started to appear. These models aim for better performance than fine-tuned models. They are also based on 70 or 72 billion parameter LLMs and were introduced in 2024 to 2025. The final model is smaller in size, but it is a general-purpose Japanese LLM trained completely from scratch. It was developed by National Institute of Informatics in the Cross-Ministerial Strategic Innovation Promotion Program led by the Japanese Cabinet Office. The training data included Japanese medical biology papers and clinical guidelines from academic societies. This LLM has been distributed to universities and companies across Japan. This slide shows a vision language model developed using the Japanese LLM. This model can generate both findings and impressions in response to an input image of a skin disease and the patient's chief complaint. We compared its performance with LaBa-MEDO, which is one of the major medical foundation models, and we found the Japanese VLM showed significantly better performance than LaBa-MEDO. So such result clearly says models trained in Japanese are more suitable for use in the Japanese medical field. Next, I would like to talk about the future of medical foundation models. This perspective paper, published in Nature in 2023, discusses the future of generalist medical AI based on foundation models. It explains how foundation models can become general-purpose tools for medical reasoning and support. A generalist medical AI, or GMAI, is trained on various types of medical data, such as images, text, signals, and audio. It also connects to different sources of medical knowledge, allowing it to perform a wide range of reasoning tasks. As a result, it can support many applications, including patient chatbot, grounded radiology report, and bedside decision support, and so on. This slide shows three potential applications of GMAI. First, bedside decision support. AI says insulin required. Medical staff ask why. AI answered to correct hyperkalemia. Second, grounded radiology report in the left bottom panels, where each sentence can be linked to a specific part of the image. Clicking the sentence highlights the relevant anatomy. Third, augmented procedure in the right panel. GMAI may be able to classify completely new medical conditions that it has never seen before. As these examples shows, GMAI could play a key role in the future of medicine and may even change the quality of healthcare itself. Another recent paper introduces many possible applications of medical foundation models. Those include medical decision-making, clinical coding, report generation, medical robotics, translation, education, mental health support, and answering medical questions. These papers indicate researchers are already underway for each application. Although performance is not yet good enough for full clinical use, I expect these technologies to be used in actual medical practice in the near future. Finally, I'd like to talk about some challenges related to medical foundation models. Foundation models are very powerful and can be used in many ways, even exceeding human performance in some cases. Because of this, they can have a huge impact on medicine. Today, I will focus on two important issues, validation and bias. First, medical foundation models need to have very high performance. It must be more accurate and cost efficient than traditional methods. This must also be true when AI is combined with doctors, as seen in the example of Flamingo CXR. Second, hallucination must be minimized. The AI should not generate information that is false or misleading. Third, there is still no standardized way to evaluate these models. General metrics like BARD score or ROUGE may not be appropriate for high-risk medical applications. We need dedicated evaluation methods that reflect the specific risks involved in medicine. The next slide will focus on hallucination in more detail. Hallucination refers to the generation of plausible but incorrect or unverified information. At the beginning of this lecture, I showed these movies where a signboard looked like it had Japanese writing. But if you looked closely, the characters were strange and did not match Japanese or any real language. These are images of hands generated by Stable Diffusion. At first glance, they may look fine, but if you look carefully, you will notice something is wrong. On the left, the right hand has only 4 fingers. In the center, the fingers are too short, and there is even a fingernail on the palm. On the right, the fingers and legs are strangely mixed. This shows that hallucination can create images that look realistic at first, but are actually medically unnatural. Here are some examples of hallucination in clinical settings. The first example shows incorrect patient management. The second shows a treatment that the patient never actually received. The third is a case where the lung were mistakenly identified as the heart. These kind of hallucinations can lead to serious errors. Hallucinations can take many forms: factual errors, outdated references, spurious correlations, fabricated sources or guidelines, and incomplete chains of reasoning. In the next slide, I will show how hallucination was evaluated in high-risk medical tasks using different foundation models. This chart shows hallucination rates and clinical risk levels based on expert annotation. The evaluation was done using 3 reasoning tasks from the NEJM medical records. Clinical risks were rated on a scale from 0, no risk, to 5, catastrophic. They tested 5 models: O1 Preview, Gemini 2.0, GPT-4o, Gemini 1.5, and 3.5 Sonnet. The 3 tests were chronological ordering, lab test understanding, and differential diagnosis tests. As you can see, GPT had the highest hallucination rate overall. In contrast, O1 Preview and 3.5 Sonnet with high reasoning capabilities showed much lower hallucination rates. Gemini 2.0 had fewer hallucinations than GPT-4o, but some of its outputs were rated as catastrophic. So detecting, evaluating, and reducing hallucinations are extremely important. Next, I will explain how hallucinations can be detected. There are 3 common methods to detect hallucinations. First, factual verification. This breaks down complex claims into sub-questions, retrieves related documents from the web, and checks the truth of each part. Second, summary consistency. This checks whether the summary matches the original content. It includes 2 types: question answering based and entailment based method. QA based method generate questions from either the source or the summary, and then verify consistency. Third, uncertainty-based detection. This approach assumes hallucination happened when the model is unsure. It uses things like sequence log probability or semantic entropy to measure uncertainty. Next, to evaluate how well models avoid hallucination, dedicated benchmarks are very useful. On the left, MedHeart, which includes similar tests: false confidence, none of the above, fake question, and memory hallucination. On the right is a benchmark that checks reasoning ability. For example, in the chronological ordering test, the prompt is, given the presentation of the case, please organize the key medical events. This test checks whether the model understands and preserves the correct sequence of events. There are several methods for mitigating hallucinations. First is RAG, Retrieval Augmented Generation, which uses external medical knowledge during generation. It allows access to up-to-date information, but may still return incorrect citations. Prompt engineering, which crafts the input prompt carefully using techniques like chain of thought reasoning, verification request, and source citation. Constrained decoding, which limits the output to predefined medical vocabulary or structure. Fine-tuning, which trains the model with high-quality curated medical datasets. Self-reflection, which makes the model iteratively improve through answer generation and information gathering. Each method has strengths and limitations, but together they help reduce hallucinations. Next, I will talk about bias in medical foundation models. When thinking about bias, we must consider both equality and equity. Equality means everyone receives the same support, even if their needs differ. This is shown by giving everyone platform on the same height. Equity, on the other hand, means adjusting support based on individual needs. Here, people receive different sized platform, so they all have equal access. When addressing bias in medical AI, we must carefully decide what kind of fairness we are aiming for. There are four main types of bias in AI models: human-induced bias, data bias, algorithmic bias, and model deployment bias. Bias can also occur in every phase of the AI model lifecycle. There are 6 phases: conception, data collection, pre-processing, in-processing, post-processing, and post-deployment surveillance. Due to the time limitation, I will focus on data bias in the data collection phase. Now we have a question. Are medical AI datasets collected evenly across the world? The answer is no. They are heavily biased toward a few countries like the United States, China, and United Kingdom. Even though data can be shared online, the fact many datasets mainly include certain racial or ethnic groups may lead to serious bias in model performance. One common example is representation bias. This happens when the training data doesn't represent all parts of the target population. Some groups, by gender, age, race, ethnicity, or other factors, are underrepresented. Here is one example. In a deep learning model trained with the UK Biobank cardiac MRI dataset, the data was not balanced across races. As a result, the model had lower segmentation accuracy for racial and ethnic minority groups compared to white participants. To reduce representation bias, we need to collect data from a wide variety of sources. This includes different geographic locations, healthcare systems, and diverse patient populations. Although I have discussed similar challenges, it is difficult to fully understand and address all of them. Some commercial models are closed and don't provide enough information. This makes it hard to assess how serious these problems are in each model. To solve this issue, the Transparency Index was proposed in 2023 and updated in May 2024. It helps users evaluate whether a foundation model is safe and trustworthy. This index has 100 items and has been used to assess 14 different foundation models. The first 32 items are upstream indicators. They assess transparency in the development process. For example, what data was used, what computing resources were used, and how human labor was involved. The next 33 items are model indicators. These cover the properties and functions of the model, such as how it can be accessed, what are the limitations, and what risks it may pose. The final 35 items are downstream indicators. These evaluate how the model is released and used. They include distribution methods, usage policies, data protection, and social impact. The paper summarized the result as follows. Among the 14 developers, 11 scored below 65 out of 100. This shows a clear lack of transparency across the ecosystem. The best developer scored 85 points, while the lowest scored just 33. In the future, it will be important to select foundation models based on transparency scores like these, evaluate the risks, and take proper countermeasures. Today, I introduced the recent medical foundation model through the contents shown in this slide. I would like to conclude this presentation with a few more epilogue slides. You may have heard of the idea of AI singularity. Some people say that AI will surpass human intelligence by the year 2045. That is still 20 years away. But do we really need to wait that long? Let me show an article in IEEE Spectrum published in July 2025, which says large language models are improving exponentially. Their capabilities double every 7 months. By 2030, the most advanced LLMs should be able to complete a software-based task that takes humans a full month of 40-hour work week. The example includes starting a new company, writing a novel, or improving another LLM. Here is another surprising example. The first Ph.D. level AI agent has already appeared. Humans only provide a simple prompt written in lead. Novel jailbreaking methods. The AI did everything else. It defined the research direction, designed the method, ran the experiment, and presented the paper. Eventually, the paper was accepted by the top conference with an acceptance rate of around 20 to 30%. In addition, the first international conference with AI agents as participants will be held in 2025. We are entering a new era where AI will debate with other AI and advance science without humans. Change is coming fast. The singularity may arrive sooner than expected. Human may lead until the singularity, but after that, we might lose control. So it is important to have serious discussions and create strong rules now. Some people may feel anxious about this. To overcome the anxiety, we need to acquire accurate knowledge and take proper countermeasures. Zero trust policy may become one of the key concepts to prevent humans from being dominated by AI. The singularity may arrive earlier than we expected. So It is important to understand technology correctly, fear its risks properly, and take appropriate action. That concludes my lecture. Thank you for your kind attention.
Welcome to IEICE's new Multilingual Translation Platform for our web services. IEICE publishes 9 peer-reviewed journals monthly in Japanese and English. This multilingual translation platform currently features 4 English-language journals. During the trial period, anyone can access this high-performance service. To start, visit the IEICE website, right of the slider, or go to Transactions Browse Multilingual Translation Trial site. The page displays 5 supported journals and top 10 most accessed papers from 2023 and 2022. To translate, select your preferred language from the flag icon on the top right. Let's choose Simplified Chinese. The page instantly translates, with paper titles now in Chinese. Notably, proper nouns like IEICE transactions, 6G and 5G, remain unchanged. Let's take a closer look at the top-ranked paper. The authors' names, acronyms like AI, ML, Beyond 5G, and proper nouns are not translated. Unlike many journal sites that offer PDFs, this service provides full HTML with formulas, making multilingual translation possible. Found an interesting paper? Want to share it? Use the share icon to spread the word. Hover over the share icon to see 4 options: email, Facebook, X, and Line. Let's click the email icon. It auto-generates an email with the paper's title and DOI for easy sharing. You can also share via Facebook, X, or Line. For more details on this advanced platform, click the How It Works tab. Experience IEICE's cutting-edge multilingual translation platform and boost the global impact of academic research.